Hi, this is Steve Williams with Track. I'm here with Kevin Dial at American Standard Circuits. Kevin is the new ASC expert at embedded passives. So we want to have a little chat, kind of Kevin's coming out party, and then we're going to talk about some specifics in some of the embedded passives and some of the pros and cons of using this technology. So Kevin, why don't you tell us a little bit about your background?
So this is my second year here at ASC. I came here straight out of undergraduate.
Okay.
I was a chemical engineer by training from the University of Iowa. I also studied chemistry and business administration there, so I got a pretty broad education with some good focus on chemical processing.
Excellent.
Some undergraduate research in electrochemistry as well, which was what kind of piqued my interest in circuits per se. There's a lot of electroplating, electroless plating that goes on here, so kind of a good fit from the get-go.
We talked earlier that chemical engineering is probably the perfect fit for a process engineer in this business, and you probably fit that bill perfectly with your educational background and some of your research, and kind of led to this process engineering position. So tell us a little bit about your responsibilities there.
So I have a pretty broad set of responsibilities. My core focus are what we call circuit formation processes. That starts at image formation in the yellow room, exposure, dry film lamination, up through electrolytic plating and etching of outer layers as well as inner layers.
Okay.
I do some dabbling in final finishes as well and some other of our wet processes, but like I said, my core focus is really making sure that we have our reliable artworks and via formations.
Okay, so you're involved in the whole imaging process, like you said, image formation, and that encompasses a number of departments here.
Right.
So you work with the, department leads, supervisors, the operators. You get your hands dirty and out there, making printed circuit boards every day.
Right. Yeah, I got Smurf hands from sticking my hands in the ammonia etcher.
So what surprised you the most about the printed circuit board process?
I think it started when I first got on site and I saw what would eventually be my responsibilities. There's a really broad set of chemical disciplines. It starts with photochemistry in the yellow room, where we've got cross-linking polymerization, up through electroless plating in our electroless copper process when we're first forming our Z-axis electrical connections. I wasn't super familiar with electroless processing, but it made sort of sense in my brain that, hey, you just need a oxidizing agent and reducing agent, and boom, you can plate metal. So, and then obviously up through electrolytic plating, where I had a little bit more background in copper and palladium. So just seeing everything that goes on in this shop and in the industry, it kind of showed me that I'm not confined to just looking at a corn ethanol reactor for 12 hours a day. I can go and I can explore a bunch of different areas and have a lot of different interests.
Right. And every day is different. And I can guarantee you are not going to get bored in this job. Your customers, it's always surprising when a customer comes in for a plant tour, and I don't know if you've gone on any plant tours with customers, but what they're most amazed at is how many process steps there are. Right? They think they can just order a board and we pull off a shelf and ship it to them, right? But everything you guys do is custom built to print.
Exactly, yeah. Especially here at what we do at ASC, there's a lot of sequential laminations where we plate and etch layers 2, 3, 4 times before they go into the final build, and we have to track our image formation, our registration, things like that multiple times. It can be really complex, but that's sort of the joy in being able to work at a circuit board. It's something new and it's something exciting every day, where I'm not just gonna have to follow yields on double-sided boards and kind of put the nose to the grindstone. There's a lot of high technology that we do, a lot of cool materials, and a lot of cool new plating chemistries that we get to work with that are really exciting.
Okay. I know you want to get into some specifics, but from a big picture standpoint, in embedded passives, what's the benefit to not only the manufacturer, but the customer of that technology?
Well, first and foremost, I'd say, being embedded, you save a lot of board space,
Okay.
obviously.
Footprint. Okay.
So that, as we move to more denser boards and more space requirements, you don't necessarily need hundreds of resistors on the surface of your board. You can bury them underneath in one of your inner signal layers that's already there. You don't need to further complicate the board. There's also some reliability improvements. You don't have to worry about as many solder joints and vias that have their parasitic electrical properties
Sure.
and reliability issues. So the focus that we have is really making sure that when our customers give us a printless specification that these resistors need to be X dimension and X resistance value, we make sure that we deliver those exactly as the customer wants.
Okay.
So that they don't have any issues with the performance of the board.
Excellent. All right. Well, I know you're a bit of an artist and you want to do some whiteboard sketching for us here today. So why don't we move on to the whiteboard and show us what you got?
Sounds good. All right. So first thing I want to sort of emphasize and address is the very basic level on what the embedded passive, its critical properties are. So we start with an inner layer, copper clad, and between the dielectric and the copper cladding we have a very thin layer of this resistor material. It can be nickel phosphorus, nickel chrome, chrome silica oxide, any sort of material depending on what the customer needs that ohm per square value to be, however much resistance they need in this resistor. The most important parameter that we deal with is the width. This in our resistor, this black area we have between two example pads, our width dictates not only our impedance, but also how much power you can put through the resistor. So if you have a high power application, you obviously need a wider resistor so that you're not going to blow it. Second is our length. The length, after we've defined our width, is what determines the actual resistance value. It's this relationship between length and width times ohms per square that gives us our final ohm value. So for example, a resistor 20 mils long and 20 mils wide with the 25 ohm per square value is going to give us a final reading of 25 ohm.
Okay.
So after we've defined our length and width, we want to look at sort of the reliability and why we might choose to bury these on an inner layer. And when I say bury on an inner layer, that comes with a little bit of a caveat in that we've also done these on outer layers. It really depends on what the customer wants and what the design needs to dictate.
Sure.
So when I talked about reliability concerns earlier, what these buried resistors allow us to do is eliminate some unreliable solder joints and some parasitic capacitances and inductances in our via structures. This is something that might come into play when you're dealing with, say, RF or microwave design, where you really need a reliable electrical property to be going through the board. And when we look at these designs, we get a lot of variation and flexibility in what the customer wants. It's not necessarily just, oh, we need to eliminate our discrete resistors. That's a big plus. It can alleviate board space, and it can drastically reduce the weight of your board if you've got a weight-sensitive application, say for aerospace. But beyond that, we see our customers get pretty creative in their designs. So for example, we can have a heater application, because when you apply electrical current through a resistor, you can actually create some heat. We can have a resistor application where we selectively introduce resistors on a track, and we can distribute this heat exactly how the customer wants. So we have heat sources in a 360-degree pattern. So recently for a customer, we buried this on an inner layer, and we opened it up in a pocket cavity. So that was sort of a nice pairing of this embedded technology with another strength of ASC, which is our machining and our other HDI.
Sure.
So another application that we saw a customer get pretty creative in was a wear sensing application, where the customer gave us a couple pads where they could take a reading. And between these pads, we had our resistor material. And as this was sort of worn away in their application, the resistance value changes.
Okay.
So as they sense the change in ohm between the two connections, they can tell that a certain amount of material has been eroded away. Once the critical ohm value is reached, alarm goes off, and they know that that this application, this piece needs to be replaced. So there's a really big flexibility in how we can apply this technology.
So that was being reduced just from being in use.
Correct.
Oh, interesting. Okay. And they had built in this test where they could monitor and know when to swap out that board.
Right.
Okay.
Right.
Interesting.
Yeah. So just sort of emphasizing the flexibility that we have with this. Not only is there a big flexibility in the application, there's a big flexibility in the materials that you can apply this to. You know, in the RF space, we've seen this on Taconic and high performance riders materials. We're working on a project with a flex material, which we're really interested in exploring because these materials can be handling sensitive. And so we have equipment and processes in place to make sure that our reliability is not in question when we process this very thin flex core. But this sort of helps enhance our understanding of what exactly our capabilities are when we process these very sensitive laminates. We can also do our standard FR4 rigid for customers that maybe want a non-high performance application, something like this wear resistance application. We also can pair this pretty well with our HDI and UHDI technology, as I talked about. We recently did a project with a customer where we drilled micro vias to this surface and plated these vias.
Okay.
So we were able to verify the reliability of this material as we create these blind and buried vias to that resistor layer without a loss in performance.
Interesting.
So now that we've talked about our buried resistors, we can move on to our buried capacitors. There's a pretty similar principle in place in that we're trying to reduce board space and board weight, but the value exists sort of in 3 dimensions rather than the 2 dimensions that I was talking about earlier. So if we have our sample board here, these materials are very, very thin as well. Not quite as thin as our resistors. They're about 8 to 22 micron in height. But what we'll generally see is them used in a decoupling capacity. So when the customer has a via in place that needs a decoupling capacitor, this can help increase that reliability and decrease noise compared to a surface mount capacitor. So we'll have the via connection from the voltage regulator. And then we'll have our connection here to our IC. And so what the customer can do is they can reduce their, they can use this capacitive material, this very capacitive material, and a ground power plane, thereby reducing their z-axis thickness, as well as enhancing the reliability of fewer solder joints and fewer vias, as I talked about with the buried resistors. Excuse me. What I'll emphasize here is that there's a little bit of a trade-off between material performance, capacitance, and handling.
Hmm.
So like I talked about earlier, ASC, we have our etchers and other horizontal equipment that's enabled to handle this very, very thin sub-mill material. And if there's a bending or change in our z-axis thickness, that can create some reliability concerns. And that's where we sort of step in and we make sure as an engineering team that the customer can rely on a very reliable, steady capacitance across their board. So the last thing that I'll talk about with capacitors is that this material, being flexible and very thin, is very sensitive to registration concerns and pre-preg lamination movement. At ASC, we've dealt with this material in the past, so we've got a good database of knowledge to pull from, and we have registration tools in place where we can continuously improve our registration so that our customers, if they have multiple capacitance layers or a very dynamic pre-preg set, they can still rely on us to be able to execute this design to make sure that we don't have shorts in our XY registration.
Okay. Excellent. And you guys build this product every day.
Right. We've done a lot of R&D orders, but we've also done a lot of volume, especially in the resistors. We did multiple thousand-piece orders for a military customer where reliability was a very big concern. So we have the infrastructure in place to make sure that we can execute this product at a large scale.
And you've got the equipment set, you've got the DFM, you've got the engineering support, and so this is becoming a standardized technology for you guys.
Right, right. We have a great engineering team that has been working with this for a number of years now. CAM and process engineering, so we're working together to make sure that we can get the customer the size reduction, the weight reduction, and the reliability improvements that they're looking for in these materials.
Outstanding. Well, Kevin, this has been super informative. I appreciate your time on this. And once again, Steve Williams, Kevin Dial for American Standard Circuits, and thanks for watching.